Yeah, today we're going to be talking about the case. It's a really common case that pops up over and over again across many domains, whether that's, you know, data science, geospatial analyses, machine learning, finance, you name it. It pops up across pretty much any domain where you want to process a bunch of cloud files, a bunch of files, whether they're stored in, you know, S3 or, stored on GCP or Azure or whatever, cloud provider you may be using. So the pattern looks something roughly like this. I'll increase that a little bit. Hopefully the text is big enough for folks. If it's not, just let me know. It looks something like this. The first step is to, well, get a list of all your data files. Today, I'm going to be working with files that are stored in S3, but everything I'm showing applies equally to, GCP or Azure as well. So you have a list of files in a bucket. Maybe this is hundreds, thousands, tens or hundreds of thousands of files. So we see a large variety of scale in the number of files you're processing. Then you define some Python function that does some processing on a single file. So this is just sort of pseudocode here, insert your actual, analysis code here. So file comes in, you do some processing of it, and you return some results. And then you just kind of churn through all the files in a big for loop. So, for file and files, get the result for a particular file, keep track of all that in some list here. After this, you now have all your results from all the files sitting there, and you do something with them. In this particular, skeleton here, we're plotting them. So maybe this is a scientific analysis, and the output of that is a plot. What that output is may look different for you. Yeah, so this is actually relatively, depending on your application, but the main sort of meat here is defining your process function. So, maybe you're training a machine learning model there, for example. Maybe you're doing some financial forecasting, whatever it is that you're actually doing, you include there. And that can be semi-straightforward to write, depending on the application, but it's often slow and it's often expensive because, when you're, if I was to fill this in with a particular application, it would, I ran this on my laptop, we would be transferring all of this data. Say I'm processing terabytes of data, we'd be transferring all of it from my cloud provider, in this case S3, to my local machine, and then analyzing it there. So that can be, like I said, that data transfer can actually be very expensive. It can really be the predominant cost for lots of different types of workflows, and it can be slow. That data transfer, depending on your internet connection too, can be really slow. So what we're going to show today is how to take this processing function here and actually run it on the cloud with Coiled. So it'll be located right alongside your data in the same cloud region, so you avoid those data transfers. So your code basically your code stays the same, but it is now much faster and much cheaper to run. When I say faster and cheaper, let me show here. So this is a blog post. We're going to show two examples today. This is almost exactly one of the second example we're going to show today. And what I want to show here is this plot that shows cost and duration of running this workflow that, again, we'll see today on my laptop. It costs roughly $25 in data transfer and takes 383 minutes. And then when I take that same code and run it on the cloud, the price drops to $1.50, and the runtime drops down to 9 minutes. There are other things you can do that I'm happy to talk about later to sort of optimize that cost as well to get it even cheaper. But the sort of main point I want to drive home here is that these aren't like 10% or 20% improvements. We're really talking about some serious, order of magnitude improvements here in many workloads. Okay, so with that, let's go ahead and dive into those two examples that I just referenced. So today, the first example we're going to show is going to be sort of a standard data loading and processing and enrichment workload that's pretty typical in data science workloads. And the second one we're going to show is a geospatial example. So again, two very different applications, but the actual pattern that looks like this is exactly the same. So the first example here, we're going to answer the question, how popular is matplotlib? So matplotlib, I'm sure if you're a Python person, which you probably are if you're here, is a very commonly used plotting library. So you hear matplotlib developers say something like 15% of papers on the archive use matplotlib. The archive, just for reference, is sort of the predominant preprint website for scholarly papers. So it has lots and millions of journal articles on it. It's free, publicly accessible, and they actually store the data for the archive on S3, so on AWS. And that it is also publicly accessible. So what we're going to do is look at that data set and see what fraction of papers use matplotlib. How we're going to tell this is starting in sort of the early 2010s, matplotlib. So basically, if your version of matplotlib is new enough, it has a watermark on it. So it encodes matplotlib in every plot, every PNG and PDF that is in every paper in the archive. So we're going to basically go churn through all of the papers in the archive, look at their data, open them up, look at the data, and see if this watermark is there. So let's do that first. Let me increase the font size here. Hopefully that's big enough. So this is, while it's publicly accessible, it's not free. Actually, the person reading the data has to pay for the access. So that's why we're setting this requester pays equals true. This is the S3 bucket where all the PDF data is located for the archive. Here I'm just showing the first directories, but it's a bunch of tar files. How many of those directories are there? There's about 7,000 of those directories. And this is a lot of data. If I sort of here get the number of bytes that are in this entire data set, I can see it's over 3.5 terabytes of data. And again, remember, like if we were to load stream all of that data down to my laptop, first off, that's a lot of data, and second off, it's going to be expensive. So let's go ahead and so that's sort of the motivating factor for moving this processing to be in the cloud to avoid those data transfers. So here we define the sort of function that we want to now map over all of these data directories to extract the information we want. The details here aren't super important. I'll point you to where these notebooks live towards the end of the webinar if you're interested in looking at some of the details. But we open up the directory. It's a tar file, so some extra care needs to be taken there to open that up. You crawl through all of the PDFs in the tar file and look to see if this special watermark is in the data. And we can define that function. And here, let's run it just on one of the directories. So here I'm running this function locally on my laptop. I'm just plucking out one of the directories kind of at random, and I'm just looking. It's going to return a big tuple, and I'm just going to look at the first 30 entries in that tuple. So here, this is taking a while because again, we're streaming the data from S3 locally down to my laptop. We'll just kind of feel that. We'll sit here and feel that runtime. Okay, so that took about 30 seconds to process, which is again one of those almost 7,000 directories. And here's what the results look like. So this paper did not use matplotlib. This paper did not use matplotlib. This paper did use matplotlib. So that's sort of the output of our extract function. It takes 30 seconds locally to analyze one of these directories. And there are, how many? This many. There are like this many different directories. I have 8 cores on my laptop, 60 seconds in a minute, 60 minutes in an hour. That would, if I was to just process all of this data locally on my laptop, it would take over 7 hours. So that's not quite, but that's almost a full workday just churning through things on my laptop to get this result. And again, it's expensive because we have to actually pay for those data transfers. So what we want to do instead is take the same exact extract function. So here I've not modified any of the code here. This is exactly the same. All I've done is imported Coiled and sort of lightly annotated this extract function with this coiled function decorator. And what that's going to do is when I run this function now, it's not going to run locally on my laptop. It's actually going to automatically spin up a VM for me on the cloud. It's going to run this function there. It's going to get the result, and it's going to return that result here locally back to my laptop. But the actual code that I run is going to look almost identical to the code before. It's really just adding this decorator. So let's go ahead and do that. I should say I've also added a couple other, there are some knobs here you can turn depending on particular application. The main one that we care about right now is this region equals US East 1. I didn't mention that before, I should have. The data set that we're reading lives on AWS in US East 1. So I want to make sure that the VM that this spins up is in that same region. And that way we avoid any data transfers there. Okay, so let me go ahead and run the function again. I'm running again on the same directory here. And I should get back the same result. And what we're seeing is we're getting some output here. Coiled is kicked in. So the first thing that Coiled is doing is it has scanned my entire local Python environment. It's found all my pip installed packages, all my conda installed packages, any Python modules I have laying around. It's packaged those up so that it can download them and replicate that same exact environment on the VM that it's spinning up on AWS. Let me go ahead and click this link here to take me to the Coiled app so I can get a sort of a better view of some other things that are going on. So here, this plot here is a time series. You can see that one VM that's getting spun up to run this extract function. You can see its state over time. So it was queued for a bit. That's the yellow. The green is starting up. The instance was running is this light blue. And we can see currently we're actually downloading all of the software that I had installed locally on my laptop. It's actually installing that same software, but now on the VM. And in this case, and you can see the region is US East 1 as I requested. Yeah, so, and it actually is up and running now, that VM, and it should be running my function. So this whole spin up VM process takes typically about a minute or two to run. So I can go back to my Python notebook here and I can see I get the same exact result. So here's the same result as I got before locally. I just did that processing on the cloud. And it took about a minute and a half. And again, that includes that VM spin up time, which was actually most of that minute and a half. Okay, so what I could do now is the same thing I had before in sort of the skeleton I showed at the beginning, is have that for loop over all the directories and process them sequentially. Instead, what I'm going to do is I'm going to use this map method. So coiled function decorated functions have a map method that's really similar to Python's built-in map function. It allows you to say, hey, take my function and basically apply it to this big list of inputs. So now I'm going to run not just over the first one directory, but I'm actually going to run over all the directories. And I'm also not going to do that sequentially on one VM in the cloud. We're actually going to adaptively scale up. So now we can see Coiled has decided to adaptively scale up to about 120 workers here. So right now I have, if I click here, I can see right now I have my one worker, which is sort of churning through these data files here, or sorry, yeah, all these directories on AWS. Now I see more VMs arriving. So now we've adaptively scaled it up, and we're going to be churning through these 7,000 directories, not on one VM, but in parallel across, in this case, over 100. And then we're gonna churn through all of these directories, and then after all that work is done, those extra VMs are going to adaptively scale down. So that scaling up and scaling down just kind of depends on how much work you've asked Coiled to do. And we're going to sit here and churn through this. It'll take, a couple of minutes, sort of to make good use of our time. I'm just going to run the rest of the cells here. What we're going to do is once we get our results, we will sort of massage and manipulate the data a little bit to get it into a form that's nice for plotting. And then we will plot matplotlib usage over time for papers in the archive. So again, that'll take a couple of minutes. We'll basically churn through all the directories here. In the meantime, I'm going to switch to the second example, go through that. And by the time we're done with that, this plot will be ready for us. Okay, so switching gears a little bit, The next example I want to show is a very different application. It's actually a geospatial one where we're looking at NASA data. So NASA publishes lots of data from its various satellites and instruments on AWS. It's actually publicly accessible. So here we're going to look at public sea level rise data from NASA, and we're going to do that using the Earth Access Library. That's for sort of accessing and finding the NASA data sets. So we're going to look at this particular data set here. We're going to look at about 20 years worth of it. And there are about 1,400 or 1,388 of these data files here. Our processing function here looks a little different than before. We're again including our coiled function decorator. The only input I want to give to it right now is that it's in US West 2. That's where I want these VMs to be provisioned, because that's where this data set lives. So we use Xarray to open the data files. We then select a particular region of interest. So in this case, the latitude longitude slices are just off the eastern coast of the US. We then do some additional data selection, data quality selections, and we return the result. So here we're going to go ahead and run this function. Again, here to start, I'm just running on this first data file. So, and we see sort of the same thing happening again. We see Coiled kicking in. We see that all my local environment has been scraped, all the pip and conda packages, and we're provisioning this VM for us. And in this case, it's actually going to be in US West 2, because that's where I've asked it to be. So I can see sort of the same thing happening here. If I go back to let's go check on that first example. Okay, we're still churning through that first example right now. So I can see all those VMs in the first example that adaptively were requested. We've adaptively scaled up, and we're just kind of humming along here at over 120, 127 VMs working in parallel. For our second example, we're currently downloading the software environment there. And then in a few seconds, we should see this VM coming online, and it'll run our NASA processing here. One thing that I wanted to show really quick is a view. One nice thing is I'm not the only person working in this account. Actually, Sarah, the person who is also on the call, was working earlier. So I can get a good sense for, so I can see my colleagues' work here. I can get a good sense for how much they're spending. Sarah did something that cost about $1.40. She was running for about 21 minutes. So this kind of visibility into usage and cost is also something, is also a big selling point for Coiled. Okay, so this VM is up and running, and here's our result. So it looks a little patchy. Again, this is, believe it or not, this is off the East Coast of the United States, but it's just on the first data file. So we're gonna use that map function again, that map method on our Coiled function to go ahead and actually process not the first data file, but actually all of the data files in the data set here. And what we'll see is we'll start adaptively scaling up here. We'll churn through things in parallel again, and we'll get our nice high resolution plot at the end. So if I go back to the first example here, we can see here's our plot and here's our results. We can see the fraction of all papers in the archive as a function of time. We can see, early on there were no papers because Matplotlib didn't have that that watermark, and then slowly and steadily, and actually pretty rapidly now, it's starting to grow in popularity. And so today, actually, anecdotally, people say like, 15% of papers, that maybe is a little dated. Maybe today we should actually update to about 20% of papers on the archive use Matplotlib. Okay, so with that, I will say thank you all again for joining. One last thing I wanted to mention was if you go to our website, coiled.io, today I've talked about these serverless functions here for running Python functions on the cloud. We have a few other APIs that I wanted to point out. We also deploy DAS clusters in the cloud for large computations. We also deploy and run Python scripts on the cloud and Jupyter Lab on the cloud. So if you're interested in seeing more examples of coiled functions like I showed today, or some of these other APIs, you can click on this use cases link here. That'll take you to a variety of examples. You know, if you're doing machine learning or just general Python or geospatial or ETL workloads, there are some hopefully compelling examples here. And then the last thing was, if you're new and haven't used Coiled yet, you can click this Getting Started button, and that'll take you to our Getting Started guide to walk you through getting set up with Coiled. From landing on this page to having your first VM spun up in the cloud typically takes about 5 minutes. So it's a pretty quick off-ramp. With that, I'll say again, thank you all for your time, and let's, I guess, jump into questions.
Great. Thanks, James. We've got a few questions coming in. So the first one is from Chris, who's wondering, so Chris has a use case where the output is actually another file to capture transform data written back to S3. So there's no result to return with each function invocation. And Chris is wondering, is there anything else to be mindful of for this type of pattern?
No, that's actually, there are sort of two modes we see. The one I showed where you return some small result, and then the one you just brought up where it's basically you load a file, you process it, and you write it out. And yeah, that pattern, you wouldn't change anything here other than, you know, there's no return. The pattern would be exactly the same. That's a great question, Chris.
Great, thanks. We also have a couple questions from Bastian, who's wondering, what are the limitations regarding the parameters of the function? So in particular, in regard to size and serialization.
Great. So I'm not sure, could you be more specific? I'll answer the serialization one, but could you be more specific about the size? I'm not sure if you're talking about something with the function or the VMs themselves, but for serialization, yeah, the function that's being decorated here needs to be serializable. Specifically, it needs to be serializable with Cloud Pickle. That's the library that Dask, all the common Dask, Spark, all the common, you know, distributed computing libraries in Python use. So it does need to be Cloud Pickle serializable.
And then I'll read your next question, Bastian, but if you have a follow-up, feel free to type it in the Q&A there. Bastian's second question is, how would you conditionally configure the coiled cluster before running the function? So for example, defining the best region, VM size through code and not hard-coded.
I don't necessarily understand the question either. Rather, if you could be a little more specific with the follow-up, that'd be great. You can. This is just I guess I don't know what you mean by I have hard coded said like region equals something. You can, for example, if you are always, it's pretty common for folks to always be dealing with the same region for, you know, if it's some private data set at their institution. I think by default, we'll use your default region for your cloud account. So there, that actually needs no configuration. But you can pipe in whatever, it's just Python code. So whatever plumbing you want to use there to pipe in things, you can. If you want to like make this a command line application that wraps this code and you say region, you know, give the command line option region something, that'll then get piped down into the coiled function, for example. That could be an API you want to use. Hopefully that helps address the question.
Great. We will move on to the next one from Fergal. So Fergal is wondering about the coiled decorator that we're using. I see. So Fergal is wondering about the configuration involved. So that decorator knows something about your AWS account details, for example. What's involved in configuring Coiled, that setup process before you start using it?
Yeah, great question. And you're right. So basically, we have to go through this. I went through the setup process earlier, which is I make a Coiled account. So I signed up. I signed up for GitHub, but you know, sign up with some whatever you'd like to here. You then need to install Coiled locally, and then on my laptop, and then I run Coiled login. And that is actually what authenticates my local machine. We also have to connect to the cloud, so to my particular cloud account. So there is these two command line options: Coiled setup. In my case, I did Coiled setup AWS, but there's also GCP and Azure. So that actually will go through the connecting my cloud account to my Coiled account. And then this Coiled login command actually authenticates my local computer to talk to my Coiled account. So then once those two steps are done, I can just use Coiled as I showed you today, and everything is all connected up to my account properly. Yeah, hopefully that helps.
Great. And then we've got another question from Chris, who is wondering if in the examples that you gave, if there's a specific parameter to say how many VMs to spin up.
Yeah, great question. So today I was highlighting sort of that adaptive scalability where things scale up and scale down depending on the workload. And there are some heuristics there to kind of have things finish in about 5 minutes. So the size that it scales up will be, bigger or smaller depending on that load to hit that roughly 5 minute mark. But you can totally configure the size of that cluster manually. I can point you to the API docs, but you can say, hey, please give me, I would like to run this in parallel specifically with, for example, 50 VMs instead of whatever is adaptively chosen. So yeah, you can totally choose that scale accordingly.
Great. Let's see, I'm not seeing any other questions coming in. Bastian, I just allowed you to talk. If you want to clarify or add in a follow-up question, you're welcome to. But no pressure.
Yeah, hi. Hello. Can you hear me?
Yeah,
Yes.
we can hear you.
Yeah, hi. So on my second question, it's basically, I think it's about the fact that you are using a decorator. So, but by the time you call the function, the decorator has been already, set up. And I'm thinking of a pattern where only at the time where you call the function what should be the parameters of the decorator. But I guess in that case, you wouldn't use the decorator, but like the coiled function that is actually behind the decorator. So I don't know if you see what I mean, because I'm having in mind not a setup in a notebook where you can rerun your decorator and adapt it, but more a setup where you are on the fly seeing what is going to be processed through your function, but you want to adapt then the coil cluster.
Yeah, I see what you mean now. Yeah,
and
that makes
by
sense.
using the decorator, then it's already sort of hard-coded into the decorator. What are the parameters?
Yeah, I think you can, I would, and that, I'm sure there are lots of ways to do this. What I would probably do is like define a function, kind of wrapping that all. So you define a function that does whatever it is you're doing in your application. You are now at the point where you know what VM you want to spin up. There you can then define your processing function with the decorator, with the appropriate sort of at runtime region or VM type or whatever the case may be for your application, and then call the function there. That's one approach I would take for that sort of, to your point, like at runtime figuring out the appropriate cloud specification. But again, I'm sure there are other approaches to doing that.
And my first question when I was mentioning the size, it was actually the size of the serialized data that you are passing through the function. So actually, I don't know what kind of limitation you have when you are sending this function from your local computer to the cloud. Obviously, you are at point limited in terms of the volume you are transferring, but I have no idea how much that is.
So we should break things apart. So I don't think there is I don't think there's a technical limit there. There is like a performance limit. You don't want to be sending 10 gigabytes worth of function, for example. So it's more of a question of performance and rather than, I think, technology.
Okay, thank you.
Yeah. Thanks for the question.
Great. Yeah, thank you, Bastian. We've got one follow-up from Chris, which, let's see, maybe was already answered. So Chris is asking if the planner is adaptively selecting the capacity to hit a 5-minute processing target,
Mhm.
and is also additionally struggling to think a little bit about the cost task completion time trade-off when there is this adaptive capacity planning.
Yeah, sure. So under the hood, we're using Dask. If you're familiar with Dask, it's a parallel computing library and distributed computing library in Python. And we're using its adaptive scaling logic. So internally, what it does is as it's running tasks, it's actually keeping track of how long each function takes to run. So it has an estimate for how long, if I run this function once, it takes a second. For example, if I run this function 100 times, it'll take 100 seconds, for example, in the, sort of the simple case. So we're sort of constantly updating that estimate for how long things take. So that's how we have that's how we have that runtime prediction capability to know how many machines to spin up to get that few minute runtime overall. So that's sort of the piece there for the how does it know how much to scale up? Hopefully that helps. And then the second question was about what is it? I'm just reading again the cost task completion time trade-off. Oh yeah, so the cost is, I mean, so basically you can stay on one machine and run 10 times the number of tasks, or you can spin up 10 machines and kind of run them all in parallel. It's not exactly the same because there is some spin up time of a couple of minutes, but that spin up time is incorporated into the adaptive scaling heuristics. Hopefully that addresses your questions, Chris.
Thanks, James. We've got another question from Pratyush, who is wondering for the geospatial example where we're concatenating the chunks at the end and then plotting them. If it's okay to concat when the size of the raster is quite large. So Sentinel-2, for example, where one tile is like 100 kilometers by 100 kilometers. Or would you again process that with a different Dask cluster?
Yeah, so yeah, it's important that in these examples where I'm actually bringing back the result to my laptop, the result is small because I am bound by the 16 gigabytes or whatever how much memory I have here on my laptop. So that sort of is key. Not exactly sure about thinking about the use case you brought up, but yeah, actually whether or not we're using Dask or not, whether or not we're using Dask or a large Dask cluster or the coiled functions here, the result always needs to, that you bring, if you materialize the results and bring it back to your laptop, it always needs to be, small enough to fit on that machine that it's getting brought back to. So anyways, I feel like I'm not exactly answering your question, but hopefully it's helpful. If you have a follow-up or clarification there, feel free to include that in the Q&A.
Yeah, maybe we'll wait another few minutes. If folks have additional questions that they want to drop in the chat.
And then briefly, I mentioned I would share where those examples are. So we have a coiled examples repo that I will throw into the chat.
Yeah, I also shared
great.
links to the
Perfect. You already shared it.
specifically, yeah, the two specific examples. But yeah, there are a lot more in that
Okay,
coiled
great.
examples repo for folks.
Yeah, so there's the repo there. Yeah, if you're curious about other use cases. Cool. And looks like Pratyush said that works. Looks like I answered the question. Great. Okay. Well, again, thank you all for coming, and we'll see you next month.